Imagine you are standing by a perfectly still pond. The water is as smooth as glass, reflecting the sky above. Now picture two massive stones dropping into the water at the same time, far away from you. You wouldn't see the splash immediately, but you would see something else. Ripples would begin to spread across the surface, traveling outwards from where the stones hit. These ripples are a message, a sign that something happened. They carry information about the size of the stones and the energy of their impact. This is a simple way to think about gravitational waves. They are ripples, but not in water. They are ripples in the very fabric of space and time itself. For most of human history, we have explored the universe with our eyes. We built bigger and better telescopes to look deeper into the cosmos. We used light in all its forms, from visible light to radio waves and X-rays, to paint a picture of the universe. Light has shown us beautiful nebulae, distant galaxies, and the fiery birth and death of stars. But light has its limits. It can be blocked by dust and gas clouds. Some of the most violent and fascinating events in the universe happen in complete darkness, producing no light at all. This is where our story begins, with a new way of sensing the cosmos, a way that doesn't rely on seeing. It relies on feeling the vibrations of space-time. These cosmic ripples are incredibly faint. They are generated by the most cataclysmic events imaginable, things like two black holes spiraling into each other and merging into one. So what kind of messages are these cosmic ripples carrying? They are not just random noise. Each gravitational wave is a unique signature, a specific whisper that tells a detailed story about its origin. The shape of the wave, its frequency and amplitude, is like a fingerprint. By carefully analyzing this shape, scientists can work out exactly what kind of event created it. They can determine the masses of the objects involved, how fast they were spinning, and how far away they were when the event happened. It is like being a detective, piecing together the details of a cosmic crime scene that occurred millions or even billions of light years away. For example, the very first gravitational wave ever detected back in 2015 told a truly remarkable story. The signal was a chirp, a wave that quickly increased in frequency and strength before abruptly stopping. Scientists at LIGO analyzed this chirp and figured out what it meant. It was the sound of two black holes, one about 29 times the mass of our sun, and the other about 36 times, spiraling towards each other. Let's go back to our pond analogy. Imagine space-time as the surface of a vast cosmic pond. Albert Einstein was the genius who first figured this out. He told us that massive objects, like stars and planets, create dips or curves in this pond. Think of placing a bowling ball on a rubber sheet. It creates a dimple. That dimple is gravity. Planets orbit the sun because they are following the curve in space-time created by the sun's immense mass. Now, what happens when objects in this pond move? When massive objects accelerate, they disturb the fabric of space-time around them. They create ripples that travel outwards at the speed of light. These are gravitational waves. Think of two black holes, each many times more massive than our sun, locked in a deadly dance. As they spiral closer and closer, they whip around each other at nearly the speed of light, churning up space-time into a frenzy of powerful gravitational waves. So a gravitational wave is a message, a disturbance sent across the cosmos. It's born from violence and carries the story of its creation. To truly grasp what gravitational waves are, we need to think about space-time in a new way. Einstein's theory of general relativity combines the three dimensions of space, length, width, and height, with the fourth dimension, time, into a single interwoven continuum. This isn't just a clever mathematical trick. Space-time is a real physical entity. It can bend, it can twist, and it can ripple. Imagine space-time as a giant, stretchy sheet of fabric pulled taut across the universe. Every object with mass sits on this fabric, causing it to sag. The sun is like a heavy cannonball, creating a deep well that traps the Earth, a smaller marble in orbit. The Earth, in turn, creates its own smaller dimple that traps the moon. Gravitational waves are what happen when this fabric is violently shaken. As two black holes spiral together, they are like two heavy balls being swung around on the rubber sheet. Their frantic motion sends shudders or waves across the sheet. When a gravitational wave passes by, it literally alters the distances between objects. This stretching and squeezing is what we try to detect here on Earth. So we have these incredibly faint ripples in space-time created by cosmic cataclysms. Why should we care? The answer is simple. Information. For all of human history, astronomy has been like watching a silent movie. Gravitational waves are the soundtrack to the universe. They are a completely new and independent source of information. Unlike light, they are not easily stopped. They travel through dust, planets, and stars as if they weren't even there. They arrive at Earth pristine and unchanged, carrying a pure message directly from their source. This allows us to probe the universe's most hidden corners, the hearts of supernovae, the collisions of black holes, and maybe even the echoes of the Big Bang itself. Every time we've opened a new window on the universe, we have found things we never expected. Now we have opened the widest window of all. We are no longer just looking at the universe, we are listening to its vibrations. This new sense allows us to test Einstein's theories in the most extreme environments imaginable. Ultimately, these ripples matter because they connect us to the fundamental workings of the cosmos. So where do these universe-shaking ripples come from? They are not born from quiet, everyday cosmic events. To create gravitational waves powerful enough for us to hear across billions of light years, you need a cosmic forge. You need events of unimaginable violence and scale. You need colossal masses moving at truly breathtaking speeds, close to the speed of light. The process often begins with the death of a massive star. When a star many times larger than our sun runs out of fuel, it can no longer support its own weight. Its core collapses under its own immense gravity in a fraction of a second. What's left behind is an ultra-dense core. If the original star was big enough, this core becomes a neutron star. If it was truly gigantic, gravity wins completely and the core collapses into a black hole. Often massive stars are born in pairs, orbiting each other for millions of years. When they both die and leave behind two black holes or two neutron stars, the stage is set for the ultimate cosmic show. These pairs continue to orbit each other in a ghostly silence, slowly losing energy by radiating faint gravitational waves. They spiral closer and closer together, faster and faster, in a final frantic dance that will culminate in a collision of unimaginable power. Let's focus on the most powerful sources of gravitational waves we know of, merging black holes. These are the heavyweights of the universe. Imagine two objects, each 30 times the mass of our sun, but squeezed into a space only a few dozen kilometers across. For millions of years they circle each other, silent and invisible. But their dance is not eternal. With every orbit, they radiate away energy in the form of gravitational waves. Their orbital speed increases dramatically as the distance between them shrinks. They go from circling each other once every few minutes to whipping around each other hundreds of times per second. In the final moments, they are moving at a significant fraction of the speed of light. This is where things get truly extreme. Space-time itself is churned into a violent storm. The gravitational waves they emit become furiously strong and rapidly increase in frequency. The climax of this dance is the merger. The two event horizons touch, wobble, and in a fraction of a second, combine to form a single, larger black hole. In that final cataclysmic moment, a huge amount of their mass is converted directly into pure energy. For a brief moment, this single event can radiate more energy than all the stars in the observable universe combined. This final burst of energy is what travels across the cosmos to us. Black holes are not the only cosmic dancers capable of making a splash. There is another, equally fascinating type of event, the collision of two neutron stars. Neutron stars are the densest objects in the universe that we can still observe directly. Imagine taking our entire sun and crushing it down into a sphere the size of a city. A single teaspoon of neutron star material would weigh about 1 billion tons. Just like black holes, neutron stars can be born in pairs. They too will spiral towards each other over millions of years. But unlike a black hole merger, a neutron star collision is not a clean, dark affair. When they collide, the result is messy. The two stars tear each other apart in a cataclysmic explosion known as a kilonova. This explosion is one of the most violent events in the universe. This is where multi-messenger astronomy truly shines. The collision produces two distinct signals. First, there is the gravitational wave chirp from the inspiral and merger. But at the same time, the kilonova explosion blasts out light across the entire electromagnetic spectrum. The intense heat and pressure in a neutron-star merger create the perfect conditions for rapid neutron capture. This is the cosmic factory where most of the heavy elements in the universe are forged. The gold in your wedding ring was likely born in the heart of a neutron-star collision billions of years ago. Once a gravitational wave is born in the fury of a cosmic collision, its journey begins. This is not a short sprint. It is an epic marathon across the vastness of the universe. These ripples in space-time expand outwards from their source in all directions, forming a perfect sphere of influence that grows at the speed of light. Imagine the merger of two black holes, a billion light-years away. The colossal burst of energy from that event starts its journey towards us at the same moment that back on Earth, the first primitive multicellular life might have been forming in the oceans. The waves travel through the cosmos for a billion years, a silent messenger on an impossibly long voyage. Unlike light, which can be blocked, scattered, or absorbed, gravitational waves are the ultimate cosmic travelers. They travel across the cosmos almost completely unimpeded, carrying pristine information from their source. The journey across a billion light-years does not garble this message. The wave that arrives at Earth today tells us the precise story of a cataclysm that happened in a distant galaxy when our own solar system was still young. The marathon runner finally crosses the finish line carrying its precious information. The journey of a gravitational wave is long, but it is not entirely without consequence for the wave itself. As the ripple expands outwards from its source, its energy is spread over a larger and larger area. The thunderous roar from a black hole merger a billion light-years away has faded to the faintest of whispers by the time it reaches our cosmic neighborhood. This is the central challenge of detecting gravitational waves. We are trying to hear a whisper from across a crowded and noisy stadium. The universe is full of vibrations and tiny tremors, from local seismic activity on Earth to the gravitational pull of the sun and moon. The wave that washes over Earth from a typical black hole merger causes a distortion far smaller than the nucleus of a single atom. For decades, this incredible faintness led many scientists to believe that direct detection was a hopeless dream. Finally, after its epic journey across the cosmos, the gravitational wave arrives at its destination, our planet. As the wave washes over the Earth, it does something very specific. It stretches and squeezes the fabric of space-time and everything within it. Imagine a plus sign. As the wave passes through, it might first stretch the vertical arm while simultaneously squeezing the horizontal arm. This effect happens to everything the wave passes through. Of course, the effect is so small that we could never feel it. If a gravitational wave stretches a 4-kilometer-long object, the change in length is only about 1/10,000th the diameter of a proton. To capture this tiny jiggle, scientists had to build the most sensitive rulers ever created. These are not physical rulers made of wood or metal, but rulers made of light. To hear the faintest whisper from the cosmos, you first need to create the quietest place on Earth. The jiggle of space-time caused by a distant black hole merger is billions of times smaller than the vibrations from everyday life. The first task, therefore, was to build a machine that could isolate itself from our own noisy planet. This machine had to be a sanctuary of stillness in a world of constant motion. The solution was LIGO. There are 2 LIGO detectors in the United States, one in Hanford, Washington, and another in Livingston, Louisiana. They were deliberately built thousands of kilometers apart. Inside each facility, the quest for quiet becomes even more extreme. The core components of the detector are protected by one of the most sophisticated vibration isolation systems ever designed, reducing seismic noise by a factor of 1,000,000,000,000. Once you have a quiet place, you need a ruler. Scientists turn to the most perfect and constant thing we know of, the speed of light. The LIGO detector is shaped like a giant L, with 2 4-kilometer-long arms set at a perfect right angle. At the corner of the L, a powerful laser beam is generated. This beam is then split in 2 by a special mirror called a beam splitter. Half of the light travels down one arm, and the other half travels down the second arm. At the end of each arm is a perfectly polished mirror. The laser light bounces off these end mirrors and travels back to the beam splitter, where the 2 beams are recombined. When the 2 laser beams return, they interfere destructively, causing almost no light to reach the photodetector. Now, imagine a gravitational wave passes through. It stretches one arm while squeezing the other. This minuscule change ruins the perfect cancellation, and a tiny flicker of light leaks through to the photodetector. This flicker of light is the signal. Detecting a gravitational wave is not a solo performance. It requires a global orchestra of detectors all working together. Having just one detector is not enough. It cannot tell you where in the sky the wave came from. To pinpoint the source of the cosmic whisper, you need multiple listeners located at different points on the globe. Because they are thousands of kilometers apart, a gravitational wave will arrive at one detector a few milliseconds before the other. To make this cosmic triangulation even more precise, the LIGO detectors have been joined by other observatories around the world. In Italy is the Virgo detector, and more recently, the Kagra detector in Japan has come online. When a potential signal is detected, alerts are sent out in real time around the world. This allows astronomers to swing their telescopes into action within minutes, searching for any flash of light associated with the gravitational wave event. The moment a gravitational wave finally reaches our detectors, the real performance begins. The flicker of light recorded by the photodetector is buried in a sea of noise. Incredibly powerful computers and sophisticated algorithms come into play. Scientists have created a library of templates, which are theoretical gravitational waveforms predicted by Einstein's equations. The computers constantly compare the incoming data against this vast library. When the algorithm finds a strong match in the data from one detector, it immediately checks the data from the other detectors. If the same pattern appears in multiple detectors with the correct time delay, the alarm bells start to ring. The waveform is converted into a sound wave. This is how we get the famous audible chirp. When we listen to that sound, we are hearing the direct soundtrack of a cosmic cataclysm that happened millions or billions of years ago. When a gravitational wave finally reaches Earth and is detected by our instruments, it's like receiving a postcard from the edge of the universe. The wave itself is actually the message. Every wiggle and curve in its shape tells a specific story about the cataclysmic event that created it. This waveform is the key. The amplitude tells us about the strength of the event and its distance from us. The frequency tells us about the objects involved in the collision. A gravitational wave chirp is similar to the Doppler effect of an ambulance siren. From this single postcard, we can learn an astonishing amount. We can determine the individual masses of the two objects that merged, how fast they were spinning, the mass of the final object they created, and how much mass was converted into gravitational wave energy. By comparing the wave's strength to its intrinsic power, we can calculate how far away the event occurred. All of this is written on a single faint ripple in space-time. Decoding the message of a gravitational wave is like learning to read a universal language, written in the fundamental laws of gravity. Einstein's theory of general relativity provides the dictionary and grammar for this language. The first message ever successfully read told a spectacular story. The waveform was a perfect match for the merger of two black holes. Scientists determined that one was about 36 solar masses, the other 29 solar masses, merging into a 62 solar mass black hole. If you add 36 and 29, you get 65. But the final black hole was only 62 solar masses. In the final fraction of a second, that missing mass was converted directly into gravitational wave energy, releasing more energy than all the stars in the observable universe combined. We have heard the symphony of dozens of these mergers since 2015. We are building a census of black holes across the universe, reading the stories from the dark, chapter by chapter. The stories told by gravitational waves are not just about black holes. In 2017, the global network detected a different kind of signal. This one lasted for much longer and reached a much higher frequency than the black hole mergers. This was the story of two neutron stars in a death spiral. Just 1.7 seconds after the gravitational wave signal ended, a NASA satellite detected a short burst of gamma rays from the same patch of sky. This was the smoking gun. Telescopes all over the world frantically turned to look at the location pinpointed by the gravitational wave detectors. What they saw was incredible. They witnessed the birth of a kilonova. By analyzing the light from the kilonova, astronomers found the distinct chemical fingerprints of heavy elements like gold, platinum, and strontium. We were watching cosmic alchemy in action. The gold in your ring was almost certainly created in an ancient neutron star collision. These are the stories the universe is telling us through these faint ripples. We have learned that stellar mass black holes are more common than we thought. We have confirmed how gold is made. We have tested Einstein's theory of gravity to breaking point and found that it holds up perfectly. These are fundamental insights into how our universe works, all delivered by the silent messengers of space-time. We have journeyed from the tranquil analogy of a pond to the violent heart of colliding black holes. The detection of gravitational waves represents a fundamental shift in how we perceive reality. For all of human history, we have been cosmically deaf, seeing the universe only through the lens of light. Now we have finally opened our ears. We have been granted a new cosmic sense. This new sense is revolutionizing our understanding of the universe. The era of multi-messenger astronomy has truly begun. By combining information from gravitational waves with traditional telescopes, we get a complete picture of cosmic events. The collision of two neutron stars in 2017 was the perfect example of this new synergy. We are no longer just watching the silent movie of the cosmos. We are experiencing it in full, immersive surround sound. What this means for humanity is profound. Gravitational waves connect us to the most fundamental workings of the cosmos. They are a direct link to the engine of gravity, the force that shapes galaxies, stars, and our own existence. We are at the very beginning of this journey, like an infant just learning to recognize sounds. The first few whispers we have heard have already told us incredible stories. The discoveries that lie ahead are bound to be even more astonishing. As we stand at the dawn of this new age, the future of gravitational wave astronomy is incredibly exciting. The current generation of detectors are constantly being upgraded, becoming more sensitive and detecting many more events. In space, projects like LISA will open a completely new window. LISA will consist of 3 spacecraft flying in a triangular formation, creating a detector of truly galactic proportions, able to detect the deep bass notes of the universe. With these future observatories, we will hear a whole new cosmic orchestra. LISA will detect the gentle hum of supermassive black holes as they slowly spiral together in the hearts of merging galaxies. And most excitingly, we might be able to detect the echoes of the Big Bang itself. Gravitational waves created in the very first moments of the universe's existence could still be rippling through space-time today, carrying the ultimate message about our cosmic origins. Unlocking the universe with gravitational waves is a journey that has just started. These ripples in space-time are a reminder of the vast, dynamic, and wonderfully complex universe we are a part of. We have learned to listen to the silent symphony of space-time. The music is more beautiful and more dramatic than we ever could have dreamed. The universe is speaking to us, and we are finally ready to listen.